Let's talk about this best possible ranking thing. So the probability ranking principle says that if you take the documents and you rank them by the posterior probability of relevance, you're going to get the best ranking possible, and no ranking is going to be better than that. So before we go any further, let's take this claim and let's try to prove it. We're gonna rank documents by the posterior probability of relevance. So if DI is our representation of a document, RI is a binary variable that says whether that document was relevant or not. We want to rank the documents by the probability that it is relevant, computed based on the representation. So we're going to call it PI. So we're going to have a bunch of documents. We're going to compute a PI for every one of those documents, and then we're going to rank them in decreasing order of the PI. So what we want to show is that this ranking is actually optimal, and you cannot do any better than this ranking. So, and we're going to take it slow. First, we're just going to prove that the precision that you would expect to get at rank R, at any given rank R, for this ranking is higher than the precision that you would get for any other ranking. Okay, so and that's fairly easy. That's fairly easy to show. So, what is precision at rank R? Again, you got a ranking. You stop at rank R. Precision is how many relevant documents you had up until rank R divided by R. Okay. Now, what is the number of relevant documents up until rank R? One way to represent it is think of a sum going from rank 1 to rank R, and I'm going to have a 1 in that sum if the ith document was relevant, and 0 if it was non-relevant. Okay. That sum overall will just count how many relevant documents I had in ranks 1 through R. And then I divide that by R in front of the summation, so I will get my precision. So that's my precision. Unfortunately, I don't actually know which documents are relevant and which ones are not. Like, nobody comes in and tells me that these documents are relevant or not. But what I do have is I have the probabilities, and these probabilities are estimated as accurately as possible. So you can assume that they're sort of true probabilities. So I have the true probabilities that a document at a given rank is relevant or not. So I cannot compute the precision, but I can compute expected precision. So what is expected precision? Precision is the number of relevant documents divided by R, so the expected precision is just the expected number of relevant documents in the first R ranks divided by R. That's straightforward. And what is the expected number of relevant documents up until rank R? So we're going to use this summation again, right? So we're walking over a sequence of documents. Some of them are relevant, for them you would have a 1. Some of them are non-relevant, for them you would get a 0. Except this time, we don't know which ones are relevant and which ones are non-relevant, but it is a stochastic event. We have a probability for a document to be being either relevant or non-relevant. So with that probability, with probability pi, the document is relevant, and I would have a 1 in that element of the summation. With probability 1 minus pi, which is the probability that R equals 0, probability that it is non-relevant, I would use a 0 in the summation. Okay? So it's just 1 with probability pi, 0 with probability 1 minus pi. Right? You multiply them together, and what you get is just the sum of the pi's. Okay? So my expected precision at rank R is the sum of the pi's from ranks 1 to R divided by R. Now ask yourself, if my rank R happens to fall somewhere, and I take two ranks that are around it, right? So rank I is smaller than R, and rank J is higher than R. So suppose I take the documents in any position I and any position J, and I flip them. Would the precision go up or down? Well, we can't say about the precision, but we can say about the expected precision. Right? The expected precision is just the sum of the pi's up until a certain rank. So you're summing up the numbers up until rank R. Okay? So all the numbers to the left of R are bigger than PR. All the numbers to the right are smaller than PR. If I take any number from the right and swap it with a number from the left, I'm changing a bigger number for a smaller number. So the sum is going to go down, so my expected precision at rank R is going to go down. So the expected precision is going to go down for any ranking that is not a PRP ranking, for any rank R. Okay, great. So that's expected precision. Can I make the same argument for expected recall? What would be different? What is the difference? So the precision at rank R, it's the number of relevant documents up until rank R divided by R. The recall is number of relevant documents up until rank R divided by the total number of relevant documents. Okay? The total number of relevant documents is just one big fat constant, just like the little r, only it's going to be big R this time. Okay? So it's going to come out, and you're still going to have the sum of the PIs. So the same exact argument holds for recall. The recall at rank R is going to be the highest for the PRP ranking, and it's going to be lower for any other ranking that you can come up with. Okay, so now I know precision and recall at rank R are the optimal. What about F1? That's a giveaway, right? F1 is just a combination of precision and recall, so yes, it is going to be optimal as well. So this one is slightly trickier. What about average precision? Is that going to be optimal for this ranking? Can you come up with a ranking that has a higher average precision? And to do that argument, what you have to think about is what is average precision. You got a ranking. In some positions in the ranking, you have relevant documents. The average precision, you take precision at those ranks where you have relevant documents, you add them up, and divide them by the total number of relevant documents. Okay? Total number of relevant documents is relevant, it's a constant. So you're summing up precisions at a certain set of ranks. Now, you can make an argument, again, so suppose I swap elements I and j. All the precisions before I will be unaffected, and all the precisions after j will be unaffected as well. But if I swap any relevant documents between pi and pj, they would only suffer from that swap. So if I swap the documents pi and pj, precision at those ranks will go down. It will go strictly down. So average precision will strictly go down as well. So what that means is the PRP ranking also gives the highest possible average precision. And you can make that argument for just about any other metric that you can come up with under the sun. So if you're trying to make sense of this, so this may be slightly puzzling. Some of you, how many of you have seen Bayes error rate? Okay, all right. So at least some of you have. So in classification, again, this is a mathematical formalism that says that there is a classifier that achieves the highest possible accuracy, and the error rate for that classifier is the Bayes error rate, and there's a way to calculate that, right? And what it says is the optimal classification is when you take the joint of the class and the instance itself. At the boundary where those joints are equal, that should be your threshold. Any other positioning of the threshold is going to lead to suboptimal classifications, because you can get more false alarms per fewer misses, for example. So one way to think of the PRP, of the probability ranking principle, is it's a ranking version of the Bayes error rate. Bayes error rate makes a claim about one positioning of a threshold. The probability ranking principle makes a claim about a ranking. It says that if you arrange the documents in a certain way, you're going to get the best possible ranking. So another way to think about that, the best possible performance at any threshold that you arbitrarily set along the ranking.